session of the workshop, and we again have three very exciting talks today. My first speaker is Dr. Wouter Koolen from CWI. He was a senior researcher there in machine learning, and he'll be talking about pure exploration problems.
All right, thank you, Shipra. So I guess I found that while giving talks, it's much nicer if I have some audience. So all of you that have just turned off their cameras because of like default settings, if you wouldn't mind, I have like a panel view here where all of you can be a little stand, and it's just the experience is much nicer. So if you don't have any preference, oh, thanks very much. Oh yeah, that's glorious. All right, so hi everyone. I'll be talking about pure exploration problems. Okay, let's see. So first of all, to maybe pacify the experts, I will only talk about a small subset of issues. Namely, I'll only talk about instance-dependent results in something called the fixed confidence setting, and then I will only look at the asymptotic confidence regime. Okay, so if you don't know what that means, don't worry. And if you're upset, I don't know, you could do something else. All right, so for everyone else, let's start. So what's pure exploration? Okay, so my perception is that it's just a fancy word for statistical hypothesis testing. And if you came from the RL workshop, because that's where we are, you might be thinking about maximizing reward. But what we're going to do here is instead we're going to think about gaining knowledge. Okay, and as a statistical hypothesis testing, it's maybe of the most amazing, glorious type, because it's multiple testing, it's composite testing, it's sequential testing, and it's also active testing. All right. So what I will do is I will first go over sort of very basic pure exploration problems, and then make it more complicated. So we'll build up towards even reinforcement learning, at least a version of reinforcement learning as a pure exploration problem. And then I'll go into some recent work and tell you about some, this will be actually quite brief, but some interesting lessons learned. Okay, but that will be mostly advertising and some high level stuff. Okay, so let's first go over some pure exploration examples. Okay, so the first example is called best arm identification. And the starting point here is that we have a multi-armed bandit model. And whenever I don't want to say anything, I will always say Bernoulli, but I just say it to get rid of any questions. So for us, a multi-armed bandit model is a vector of k Bernoulli means. All right. And what can we do? What are we going to do with this bandit? Well, we're going to interact with it in rounds. And the first thing to know is that we can decide when we want to stop. Okay, if we don't stop, then we get to pick an arm, so one of these k arms, and we see a sample from that arm. Okay, so normally in a bandit, you would treat this as a reward, but we're not going to treat it as a reward. It's just one observation from this arm. Okay, so this we keep on doing until we decide to stop. And then at the very end, we recommend one of the arms. Okay, so here's that protocol again. So then one random variable that is decided by this interaction is the time at which we stop. So let's call that tau. So that's the number of rounds after which we decide to quit, right? And if we never quit, then let's say it's infinite. Okay, so now that's what a learner can do. So what is a good learner? A good learner is a learner that actually at the very end outputs the index of the best arm. Okay, well, you can't do that with certainty, so we're going to allow a certain error probability. So we say that the learner is delta PEC for some confidence parameter delta if the probability that the learner makes a mistake is at most delta, right? And this has to hold no matter which bandit we put the learner in. And what does it mean to make a mistake? Well, you have to stop. So tau is less than infinity. And you have to give the wrong answer. So whatever you output at the end is not the index of the best arm. Okay, so if you make mistakes very rarely, you're delta pack. And the other thing that we want is that you actually recommend something quickly. And we'll call the sample complexity the expected stopping time. Okay, so this is a function of mu, of the bandit that you're in. And we would like to have an efficient, so that's computationally efficient, delta pack algorithm that has, in some sense, a small sample complexity. All right. So that's that goal again. So what would it look like if you do this? And in some sense, this is like a paper template that you can reapply for all the more complicated problems. So you propose some algorithm. Okay, so that would mean you write down a stopping rule, a sample rule, and a recommendation rule at the end. And then you first show that it's delta pack, so that it qualifies as a solution. Then you maybe say, oh, I want it efficient, so you show that it's somehow fast. And then you do the difficult thing, which is to show that its sample complexity is actually small, right? And since we are going to look at instance-dependent results, we would like a bound that looks like some function of your instance, f of mu. And I already put the typical scaling here, so that will typically multiply a log 1 over delta. And then some more stuff that is small. Okay, so that's what you would like to show. And then to really sort of close the door on this problem, you would show that if you have any delta pack algorithm, you need at least a certain number of samples, right? And if that matches your upper bound, then you basically solved it, right? You can also imagine that you have some constant factor here maybe, or that you can see that as like a pre-solution stage. Yeah, I think you don't want constant factors. Okay. Good. So I just sketched you a problem and I sketched you what a solution could look like. So before talking more about solutions, let me first discuss a bunch of variations of the problem. Okay, so there are loads of variations being discussed. So I tried to make it very simple, but you can do things like make different assumptions about your arms, right? So you can say they come from some exponential family maybe that I know, or you can try to make some non-parametric assumptions. Like sub-Gaussian is common, but you can also do it heavy-tailed by just assuming some moment exists. Right? So all these give new problems in which you can try to come up with a solution. You can assume some prior knowledge about the class of bandits that you're going to face. For example, it could be linear bandit, Lipschitz. Well, you can imagine lots of freedom. You could say, I don't really have to find the best arm. I'm happy with an arm that's epsilon optimal. So you redefine slightly what it means to make a mistake. Now you make a mistake if the arm that you output has a mean that is more than epsilon below the mean of the best. Right? And you can play with what you actually observe when you interact with your bandit. So then you talk about something called feedback graphs and maybe semi-bandit framework, something like that. Okay, so all these are interesting and I won't really talk about them. What I want to do is I want to look at much more major variations of the setup. So I'll discuss Nash equilibria. I won't discuss shortest path, but you'll see from what I show you exactly how it would fit. I'll discuss tree search and solving MDPs. Okay, so just to make sure that we're on the same page, I'm only discussing problems right now. I haven't told anything about solutions. We will get there, but I'm just building up a huge stack of problems. Okay, so this is the Nash equilibrium identification problem. So what is this? So you assume that you have access to basically a, a multi-arm bandit, but it's indexed by two finite sets of actions. So you think of this as the payoff matrix of a game. And then the interaction is exactly as before, except now every round you get to pick an index in your payoff matrix, and you see a sample from the distribution that's behind that entry. Okay, so it's a stochastic payoff matrix. In each entry there is a distribution, and you have sample access to it. Right, so you interact with your bandit until you're satisfied, and at the end you output two mixed strategies, one for each player. Okay, and we say that your output is an epsilon approximate Nash equilibrium. If you've looked at two-player games, you will see that this here is the suboptimality of both of these, both of P hat and Q hat summed. So if the gap of your Nash equilibrium is at most epsilon. Okay, and then the question becomes, can I make a learner that identifies such an approximate Nash equilibrium? Right, so this is all zero sum, by the way. You can do the same, not zero sum. Well, do. You'll run into hardness, of course. Okay, so all I'm saying is this is an interesting, big, broader problem of best arm identification that we might look at and that we might try to solve. Okay, so here is another version. It's also based on games, but it's based on sequential interaction instead of parallel interaction. So here we assume that we have some game tree and that we have a Bernoulli distribution in each leaf. And we interact with the bandit by picking leaves and seeing samples. And at the very end of the interaction, we recommend one of the children of the root. So we're basically making a claim saying that in this model for a two-player game, the best action for the player in the root is to go, let's say, right. Right, so this could be an output of our learner. Okay, and then we can say, well, is the output correct? Well, the optimal move would be, you know, the min-max, the arg min-max of this tree. And you can again say, can I make a learner that outputs that optimal solution with high probability? Okay, so now let's get to the last one, which is maybe closest to the workshop, which is to solve an MDP. Okay, so we have some state space, action space, let's say a fixed start state. And what we don't know is the rewards distribution. Let's say again, it's Bernoulli, and the transition dynamics, which is some distribution that says where we're going if we do a certain action in a certain state. Right, and you can do many interaction models with your learner and your bandit. But here I picked the one where you pick a state and an action. Right, so you don't have to necessarily go there. You can just say, I want to see what this action does in this state. And then you observe, let's say, both a reward sample and a successor state sample. Right, you can keep on doing this. And at the very end of the interaction, you output a policy. So that's a mapping that says in every state which action you would like to do there. Okay, and then you can define what is actually the policy that I want to find. Well, you typically say you have to sort of talk about value functions to define it. So you define the value of each policy with the usual Bellman equation. And then you say the optimal policy is the one that maximizes the value in the start state. Okay. And then you can say, can I, with high probability, output this optimal policy? And how do I do that? How do I make a learner for that? Okay. So now what I showed you is a whole bunch of problems. Now let's talk about solutions. So I'm not sure I'm going to reach the top of the stack, but I'm going to try and build from the bottom to solve some of these problems. Check on the time. Okay. Okay, so let's go back to best arm identification and let's see how we make algorithms. And so we want to say something about the sample complexity. We want to get it small. But first, let's do a lower bound on the sample complexity. Okay, and the intuition here is that if you have an algorithm and it's doing something on one bandit model and it's doing something else on another bandit model, then the only thing that was different between the two is what the learner saw. So if it has a big difference in behavior, it must be because there was a big difference in what the observations were. Okay, so if your delta pack on some model mu and also delta pack on some model lambda where the best answer is not the same, then you have a very big difference in what you do. Namely, you recommend something completely different at the end. And that means you have to be collecting a lot of information to discriminate between those two. Okay, so let's turn that into a lower bound. So we're going to say the alternatives to mu are all the bandit models with a different best answer. And then this is sort of a very nice information theoretic lower bound that says if you're delta correct, then the sample complexity that you have on bandit model mu is some problem dependent constant times log 1 over delta. And the problem dependent constant is given by a certain min-max optimization problem, where you're actually squeezing sort of all the juice that you can have out of this argument into a lower bound. Okay, so if you haven't seen this before, I'm not going to say much more about it, but I very much like this paper, and I recommend you read it, especially the Garrivier and Kaufman one. Okay, so let's get this. So we see now that the sample complexity is governed by this max-min problem. Okay, and you can think about it and think like, what should a good algorithm do given this? And you can convince yourself that if you want to match this, your sample proportions on the arms must actually be matching this argmax. Otherwise, you're going to overshoot this lower bound. So the only way to match this lower bound is to sample with proportions, what's called oracle proportions. So this argmax for W. Okay, so this leads to an algorithm scheme, again, from Garrivier and Kaufman, where you try to do exactly that. So in each round, you try to compute W star, but you don't have mu, so you do it at an estimate. Okay, and then you try to sample in such a way that your sample counts actually converge to this estimate. And then you try to make sure that your estimate actually converges by at least making sure that the mu hat converges to mu. Okay, and then with some extra magic for the stopping time and the recommendation rule, you can show that this actually asymptotically matches that same lower bound that we saw. Okay, and if you look in the analysis, one important thing is that having the mu hats converge to mu is not enough. You also need that the W stars at the mu hats converge to the W stars at mu, right? So that's a continuity, and together you can sort of make everything chain up and arrive here. Okay. So why are we interested in asymptotically optimal algorithms? So one of the reasons is they actually work quite well. So it depends a little bit on the problem, but in some problems they have the best results that I know of. And this happens, for example, for best arm. And we also have some results, or at least a master student of mine did some results where he got the state-of-the-art Minimax game tree search results. Okay, so that's cool. So the asymptotic optimality is actually saying something even non-asymptotically. And then it's sort of a different style of algorithms. It's not confidence intervals, elimination, Thompson sampling, it's something else. Right? So it's always good to have more tools. And it says, what's really the heart of the issue? In some sense, it's computing W star. Right? So once you have that, you basically have everything. Okay, so now let's look at these interesting points that I was going to make. So these are sort of recent contributions on top of this framework. Okay, so the first thing is about that continuity. So is the oracle weights continuous? And unfortunately, it's not always the case. You can sort of fix it if you want with sort of fancy continuity, but if your problem has multiple possible answers for the same bandit, so that happens, for example, in epsilon best arm identification, then this attempts don't work. It's really a discontinuous thing. And so what we show is that you have to change your algorithm a little bit. Okay, so you can have a lower bound in the same vein, but with an extra max. And you have a different algorithm. It's slightly changed. It's sort of made sticky, is what we call it, that then matches this lower bound again. But it has to sort of bypass this discontinuity problem in a careful way. Okay, and we give some examples where if you don't do this stickiness, you're actually suffering. Okay, but then a second thing that I wanted to show you is this lower bounds are based on this max-min problem. Okay, and there is a nice thing you can do, and that is to observe that you can solve max-min problems by using online learning. So you instantiate learners for max and min, and you have them play against each other. Right, and this leads to a slightly different organization of the algorithm with two advantages. So it's faster and it composes nicer. So how does it work? You don't know what problem you're in, but you estimate it. And you plug in that estimate in every round. Okay, so you have these two online learners. They're learning on this problem, but you're changing the problem while they're going. Okay, but the nice thing is that you only need to do one round of online learning for every round of interacting with the bandit. Okay, and then you can sort of play nice games. So you can, for example, add optimism to your problem to get your exploration going. And then if you look at all the things that you have, for example, a regret bound for your learners, you did some concentration, you added optimism. All these things sort of nicely add up and get you finite confidence guarantees. Okay, so this is a nice toolbox. And you win computationally because you only have to do one online learning step in every round. Okay. So the last thing is something about martingales. So with two colleagues from India, we looked at a version of the problem where we try to identify the arm of minimum CVAR. So that's again some funny objective variation, not best arm, but best CVAR. And we try to do this in a non-parametric setting with heavy tails. And what happened was sort of a surprise is that if you look at this lower bound and you take its dual, then you get a very nice collection of martingales. And if you do the mixture method based on those, you get sort of all the deviation inequalities that you need for stopping for free. Well, not for free, but it's sort of surprisingly nice and slick. Okay, so I want to conclude with some open problems. So what I hope is that solving a few of these problems in the end leads us to understanding so much how this actually works in general, that we can make something that I sort of jokingly call the pure exploration compiler. You basically describe in some formal system what you wanted to learn and maybe the assumptions that you have, and it spits out an optimal algorithm. Right? It's crazy, but also I think it's nice as a goal to see how far we can push this. And then we also need to understand, like, in what cases these asymptotics don't kick in. And in those cases, it's very important to understand what other problem parameters are doing, and how we should maybe change our algorithms to make those dependencies better. Right? And then one motivation for looking at these problems is they appear as subroutines for larger systems, for example, for game solving or for planning. And what we should do is we should actually, look at the solutions and see how they interact with the environment, and maybe try to optimize the joint system and not just these parts. All right, thanks.
Thanks, Wouter. If there are any quick questions, please go ahead and ask them while the next speaker can set up. Lillian can set up here.
So Wouter, I really love this approach of starting from this lower bound and trying to like track the solution of that based on your estimates. But do you think that this can really scale up beyond like these discrete cases? For example, if you think about like linear bandit problems with continuous action sets, for example, do you think that this methodology is extensible to that one?
Well, I don't really know how far it can go. Some background noise.
It's the last PR of the ranger, so maybe.
So you can. Right. So one case that I do know a little bit about is when your answer set is continuous. So that is typically not really a problem if you make it into a decision version where you say, as long as it's epsilon optimal, it's good, and otherwise it's wrong. There you can do the lower bound and it's fine. Continuous actions, I think it's more complicated. I haven't looked at it yet. Yeah, maybe there are people in the audience that have tried it.
Yeah, because like in all these extensions to like game matrices and to MDPs, these always had some kind of a discrete structure in them. So I don't know. I mean, do you really see this as a fundamental limitation, or not quite? In the end, you can discretize everything and it's going to work. Like, what's your view on this? Just curious.
On that lines, like maybe it will be nice if some kind of mean field like KL divergence with some kind of mean field approximations could be utilized. Maybe that's one way to go. Yeah, I don't know.
So maybe should we keep this discussion for the session? I think there is a lot to be said around this topic. So maybe it's a great topic for discussion. Lillian, do you want to share your screen?